Hi everyone, this is the introduction to chapter 9.2, the photoelectric effect. In 1922, Albert Einstein won the Nobel Prize for his discovery of the photon. Before Albert Einstein, we thought that light was simply a continuous wave. But after his discovery, we realized that light was composed of many particles of light called the photon. Each photon has a set amount of energy that is exactly proportional to its frequency. So let's have a look at the experiment that Einstein was able to solve in order to prove that the photon really exists. So if we have a diagram here of the photoelectric experiment. So what happened is when you shine a light of a certain frequency on a piece of metal, some electron will be ejected. We will call these ejected electron photoelectron. Now in the diagram over here, we have the light flashing on a target metal. We have some electron, photoelectron, being ejected. On the other side, we have the cathode linked to ammeter, and we have a battery over here. And generally, we want to have an adjustable battery, so maybe we add some extra battery. We want to be able to adjust the voltage over here. Now, what's happening? The photoelectron are being emitted. We can calculate how many of them are being emitted, and we can use the voltage here to get a sense of the energy carried by each electron. So let's have a look at the first diagram over here. We have a diagram of the voltage versus the intensity. So the voltage measured on the battery and the intensity or the current measured by the ammeter. So what's happening in this diagram, we keep the same frequency of light, but we're changing the intensity of the light. So that means for the black line, we have a high intensity or a high power. For the red line, we have a low intensity or a low power. What we see here is that the intensity dropped to zero exactly at the same voltage. Let's look at the diagram just to see why this happened, and note that the voltage is negative. What happened is the electrons are being emitted and they are going through this space, and they are going to hit the cathode and they will contribute to the current. But when the voltage is negative, the electric field is pushing the electron on the other side. So at this point, the electric field is so strong that the electron do not have enough energy to get to the other side. Therefore, the current falls to zero. That's interesting. That tells us what is the maximum kinetic energy of each electron once they are being ejected from the metal piece. Now, if we look at the difference between the high power light or the low power light, and again, both of these have the same exact frequency, you can see that the intensity is different, but the cutoff voltage is exactly the same in this case. So if we increase the number of photons, we will have more photoelectron. But if we don't have a high enough frequency, as we will see in the second diagram, we won't have any photoelectron at all. So let's have a look at the second diagram now. This diagram is the frequency of the light versus the kinetic energy or the maximum kinetic energy. Now, if we go back in the previous diagram, we can find the maximum, the voltage at which the electrons are not able to cross that space. We can find what was their maximum kinetic energy by multiplying the charge multiplied by the change in potential. And the charge of an electron, well, is simply E. So the maximum kinetic energy is equal to E multiplied by the difference in potential energy. If we were to calculate the maximum kinetic energy for different frequency, what we would see is before a certain frequency for a given metal, there won't be any energy or any photoelectron, because the photon themselves do not have a high enough energy to eject the electron from the metal. As we increase the frequency, there comes a point where we start having a current, and if we increase the frequency further, we will see that these electrons, these photoelectrons, will have a higher and higher kinetic energy. So what's happening here? If we go back to the first diagram, we have the electron in the middle, a photon come and strike one electron. All the energy of the photon is being absorbed by the electron. This electron then is ejected, so it fights the binding energy of the metal, and then the remaining energy from the photon is transformed into kinetic energy. So the maximum kinetic energy plus a value that we call the work function, it's really the energy needed to break free of the attraction of the metal on the electron, has to be equal to the energy of the photon. The energy of the photon is Planck constant multiplied by the frequency. All right, so in the next video, we are going to be solving some example in order to clarify all of this, to put everything together. See you in the next video.